is we like to look at stability of compounds. So what we're going to learn about in the rest of this chapter is how to assess the stability of a compound. Okay? So some data first. General reaction for combustion, what is it? If it's a hydrocarbon, let's say it's C's and H's, what are you going to put with it? What's that? Oxygen, right? So you have oxygen with it. What are you going to get out? CO2 and water. Why did I write it down there? Because it's lower in energy, right? And if you remember energy diagrams from OChem or from Chem 1A or from Chem 1B, we talk about these in a lot of different OChem classes. You would draw an energy diagram, and the y-axis would be energy, and the x-axis would be the reaction coordinate. Okay. But the idea is, combustion reaction is exothermic. When you burn it, you get CO2 and water, and the other thing that released is heat, right? That heat is a direct measure of the stability of the starting molecules relative to the ending molecules. So chemists love to burn things. So here are 3 isomers of octane, okay? And their combustion, heat of combustions, so how much energy you get when you burn it. Now, it's octane. So for every single one of these, the number of CO2s that you get and the number of H2Os that you get are exactly the same. So they're going from some energy state before you burn them to the same energy state when they're done. So now what you can do is directly compare the differences in energy between the molecules when they started. Okay? So down here, this is the base energy where they ended up. Each one of these released a different amount of energy. So question. Which of those 3 molecules, the octanes, was the least stable before it was burned? They're all saturated. They all have the same formula. They're all constitutional isomers, but they have different energies. So it's not the middle one, right? The middle one's like the bad choice. If you're saying most or least, the middle one's the bad choice. That's what Goldilocks always picked. Okay? So it's either got to be the first one or the last one. So what is stability? When when you're stable, let's say you're at home, forget it's organic chemistry, and you're stable. Okay, where are you at? Lying on your bed, right? So is that high energy or low energy? That's low energy. So which one's least stable of the 3 octane isomers? The first one, because it's the highest in energy. The lowest in energy is this one. Okay? Now, think about what that means. What's different about the structures? The branching. No branches, a couple of branches, more branches. These are essentially secondary if you're considering like it was an R group, what's attached to it. And this is essentially tertiary. But the idea is this. The more branching that you get, the more stable it becomes. Now this is an electronic effect, okay? There's something to do with the way the electrons interact with the carbons that causes it to be more stable. We'll talk about that.
Is it also because the oxygen can't bond with the inner carbons as well?
No, because it's still the same carbon. It can. I mean, it obviously can. Yeah. That affects how fast it will burn, but not necessarily difference in energy. So it has to do with what we call electronic effects. And we'll get to that in a second. Okay, so the more substituted or more branched a carbon becomes, the more stable it becomes. Okay? Interesting. I always like that diagram. You have to be a little bit careful. The energy differences aren't that big. This is 5,470 kilojoules. This is 5,460 kilojoules. So it's only 10 kilojoules per mole difference out of 5,500. So it's not a lot, okay, but it's there. I'm going to skip this slide. It's all really nice and everything. Okay, and that one too. So now what we're going to do is take a look at what are called Newman projections, and that's why I have to go get my model kit. I won't be able to show these very nicely on Doceri. I think there is a way for me to take pictures and incorporate them, but it's nice that people come to the lecture. So, this is the time of the semester that I encourage you to pick up a model kit. You should have probably already had one now, but it's really not that useful to have one up until this point now. So, and it turns out all my carbons are screwed up except a few. And I have to dig through to find them. So I'm making ethane. It's all right. You made me dance. What's so bad about that? There used to be a slogan, I don't remember who it was just life is short, so why not dance? That one's a little bit better. All right. Ethane, right? This is, you could do this as wedge and hatch and wedges, or they call it wedge and dash. I've always called them hatches. They call them dashes. It doesn't really matter. You could do it as a sawhorse. A sawhorse is looking at it like this. I don't know if you can see that perspective, right? That is the sawhorse that looks like that. Or you could do it as a Newman, and the Newman looks like that, roughly. Hang on. Oh, there we go. Oh, I know. Let's do this. Looks like that. See how that goes? So what is the Newman doing? You're looking at the front of the molecule, right? And you're going to have to make some assumptions about the circles that are drawn, okay? This one comes all the way to the front, so that is the front one. And this one stops. Like if you were to actually look at it like head on like this, right? You would see like this front molecule blocks where these bonds go into here. So that's, these ones that are blue are in the back. So you have to learn a little perspective, right? Like you can learn to look at something from this side, but you could also end up looking at it from this side, and it can give you a different perspective of the molecule. So in the Newman projection, if I told you to draw this molecule from the other side, then you would have to put the ones that are in blue to the front, and they would meet all the way in the middle, and the ones in the red would be in the back, right? And it's as if you look down the bond from a different direction. When I tell you to like draw the Newman projection of a molecule like this, and we number these 1, 2, 3, 4, 5, and say, draw the Newman projection down the 2-3 bond, that means looking at it from this direction down in that direction. Okay? And then a lot of times, we like to draw these fake eyeballs that look like that with arrows coming out of them. So that's the idea. If I wanted you to draw it from the 3-2 direction, you would look from here to the end here. Okay? So perspective will be important, an important thing in drawing our Newman projections.
So if you were drawing then with the 2 hydrogens coming off of the number 2, we going up this way, from the 3 would be going down that way.
Yeah. So let me get it. So here you would have a hydrogen out in the back and a hydrogen in the front, and here you have a hydrogen in the front, hydrogen in the back, and they would be like that relative to each other. Well, it'll be easier to see if I use a model initially. So what we're going to do is we're going to draw the Newman projection for this molecule, and I'll just draw it to the right of the molecule. But I'm going to build it first. So that's got 3 carbons in it, right? So it's propyl chloride is the common name for it, or 1-chloropropane is the systematic name for it. And I need to find another carbon. This could be harder than actually drawing it. Oh, that's carbon. Okay, it's a carbon with a 90-degree bond angle. And this is going to be chlorine in green, okay? So now, you're looking down we'll call it the 2-1 bond axis. You number it from the chlorine side. Oh, wait. This is a methyl group. I need another one. Darn it. Here, I'm going to do that. It's not a methyl, but it's okay. And then I want to draw that molecule looking down the axis like that. Now, it says the chlorine is straight up, right? And then the methyl group is doing what? It's in the back, so I need to switch these two, okay? And so the chlorine's up in the back, and the methyl group is down in the front, and there's another methyl group on the hatch going into the back of the board, okay? So now, when you're going to draw this, you're going to draw it from that perspective, like that, okay? So, I actually have a harder time drawing it with the model than without the model. I think it's just from doing it for too long. Go back a second. In these other Newman projections, you notice this angle here. Oops, sorry. You'll notice that this angle here and this angle here are the same. They're drawn as 120. So when you look head on to any atom, the angles are 120, okay? Now when I look at this molecule, you notice that part of the molecule is drawn all in the same plane. It's drawn in this plane. You notice there's not a hatch or a wedge on those. So those are lining up with your eye. And they're in the middle of the molecule going straight up and down. Does that make sense? They're all in the plane, and I'm looking down the edge of the paper. You think they could have got a better eye for this, by the way? That's an eye. Looks like a squid eye. So when you're looking down like this, these are all in the same plane. So when you're looking at it, they're vertical. Okay? So now, in drawing that, I would draw a circle like this. And this is the front carbon. Okay? There's a methyl group going straight down. In the Newman, that's that guy. So those are the same guy. Actually, you know what? Let me do this. I drew a little too close to it. Now, what is the angle that we always draw the other groups at? 120. So you draw the other ones in. These are at 120. These are hydrogens. Okay. Now, that's the front. In the back, the Cl is going straight up. So the Cl goes like that. So this is going to be Cl. That's this guy here. Now, where do the other ones go relative to that? 120. And then this is the tricky part, okay? I'm looking at this molecule like this. My thumb is where the eyeball is looking. Where's this methyl group in relationship to my hand? Is it on the palm side or the back side? It's the back side of my hand. Now I'm looking at my thumb, right? Where's the methyl group going? It's in the left, right? Because you're going like this, and then you look at it, this has got to be the CH3 group that's down here. Because when you use your hand, right, to look at it, and you pull it off and you look at it, it's on the back of your hand. Yeah, I should. I got distracted by having to erase it. So that's the Newman projection for that molecule. This molecule is said to be in the staggered conformation. Because they go between at 60-degree angles. It's always the bond in the front splits the angle of the bonds in the back. So it's staggered.
So that is called staggered, right?
Yeah, that's a staggered configuration. We'll call it a configuration. It's not a conformer. It's not a constitutional isomer. It's what we call a conformer. It's got a different rotation of a type of rotation on a bond. Because remember, this bond here is a single bond. So these groups are always rotating around. And what we're going to end up doing is analyzing what the energy of the molecule looks like as the bond rotates around in the back or in the front. Okay? Okay. So, real quickly, you guys remember Vesper Theory? What does Vesper stand for? Valence shell, electron pair. What's the R? That's the important word. Repulsion, yeah. Right? So, why would an angle from Vesper Theory, because you know you learned the 109, the 120, 90s, all those things, the angles, 180s. Why would the angle matter in terms of stability? Yeah, the electrons are repelling each other. So what do the molecules always try to do to be more stable? Far away as possible. So that's why if you take 4 groups, right, and put it on a carbon, it's not 90-degree bond angles. They move into 3 dimensions to create that 109.5 degree angle. So that what that does is increase the distance between the atoms, and the atoms have electrons in their bonds, and they have electrons in their orbitals, and those repel each other. So thinking about Vesper theory, right, the angle or the distance between the groups on the atoms affects the stability. So if the angle looks like it's split 60, right, degree split from between the front and the back like that, that's as far away, what we're showing here in the staggered configuration. Sorry, let me write this down. 60, this is 60. That's as far away as a hydrogen can get away from another hydrogen in this molecule. Now remember, the molecule can rotate. And I think I've mentioned this before. In a molecule like ethane, it's going around 1,000,000 times a second that it rotates around. It goes around this thing like this all the time at room temperature. Okay, this angle is got a name, and this angle affects the stability, and it's got a name. It's called the torsional angle. That's that word that's here. What does torsion imply? It implies twisting. And so when you take 2 objects, let's say like my hand's like this, okay? The torsional angle between them is 0 right now. And then it becomes 180. That's a 180-degree torsional angle. It's the angle, right, between the plane created by this hand and the plane created by this hand. So a 60-degree torsional angle is about like that. 120 is about like that. Sorry, like that. That was about 60, 120. Let's see. And then what is this one over here? 120, 240? Yeah, and then 360 like that. Okay, so those are the torsional angles. It's the angle between the planes created, if you think about it, torsional, the angle here, right? Those are the three atoms, they define a plane, so that's like one hand. And then there's three atoms, they share two atoms. This is the three atoms that create another plane. We're looking at the angle between the plane created by this group and this group. So right now, what's that angle? 0, and then it's about 60, and then it's about 120, 180, okay? So the torsional angle is what we call the angle that's, we call these, terminology. We call the angle between two planes the dihedral angle. Okay, that's the name of it. Yeah, so when you're looking at a torsional angle, you're always looking at 4 atoms. It's the 2 on the end and then the 2 that connect them. Okay. Okay, so as the molecule rotates, let me get back to ethane. Broken hydrogen. So 60, right? And then this at room temperature begins to rotate. As they rotate, what happens to the distance between the hydrogens? They get closer. And that makes sense. As the angle closes, the distance closes, and then the angle begins to increase again. Right? So the distance increases. The Vesper theory tells us what about the energy of the 0 angle versus the 60 angle? Which is higher? 0, because they're closer. So Vesper is, if they're close together, right, it's high in energy, so molecules like to rearrange their atoms to be further apart. And what we're talking about is this energy created by the torsional angle. It increases as they get close together, decreases as they get further apart. It's the same concept as Vesper theory. Okay, so those are close together. These are farther. There's a lot of other conformations that are possible, right, as you change the angle degree by degree by degree. And so what they like to do is actually simulate or measure that energy, and it looks something like this graph here. So at 180, we're going to identify these. This is staggered. And then at 120, it's eclipsed. Right? And that pattern is all the ones that are at the top are eclipsed, and all the ones that are at the bottom are staggered. The difference in energy is about 12 kilojoules per mole. Now, how many hydrogens are interacting, though? There's actually 3 pairs of hydrogens interacting for that, right? So on average, every hydrogen-hydrogen interaction is about 4 kilojoules per mole.
And that's for every hydrogen?
Every hydrogen-hydrogen interaction, yeah. And if you have the slides, it's actually, they calculate it on the next slide, but there's so much room here. Okay. So it turns out, maybe you guys don't want to do this, delta, oh, sorry. You guys remember this? Delta G is equal to minus RT ln K EQ. No! I'm not going to make you do it. Oh, no, it's not hard. You stick 12 kilojoules per mole in here, and you divide by R and T, and you get the equilibrium constant. And what you're going to find out, okay, is the equilibrium constant is going to tell you that 99% of the molecules are the staggered conformation at room temperature. And the rest of them are transitioning between staggered configurations. Like they're like sitting like this, right? 99% of the time, and they get enough energy, and then they slip past, and they go like this, and they slip past. And they do this like a million times a second as they go around and around. But 99% of the time, the molecules are in the staggered conformation versus the eclipse conformation, and that's only for 12 kilojoules per mole. Okay. So let me ask you the. Oh yeah, I forgot about that. I'm going to skip this next slide, by the way.
So then is there only staggered and eclipsed, or?
We only look at the staggered and the eclipse, and we assume continuity in between. Right? So we don't have to calculate, well, what is it? Because you could, I guess, if you wanted to, say, oh, here's an angle. This is the force created at this distance. This is a new angle. The distance is now this, and you can use Coulomb's law to determine how much energy there is. But we have computers to do that. The program called Spartan, and I would love to use one of these days in lab. I'm not sure we'll get it in. But what it'll actually do is take a molecule and rotate it through all the conformations and calculate the electrical repulsion between all the groups on the atoms. And so you can get this diagram. It'll generate it for you automatically. Now, when we do it, I'm going to make you do each angle individually and then assume continuity in between rather than let you have the computer do all the work for you. Okay, so
But why does it spin?
oh, because it has energy.
Is that only
Yeah.
just because the electrons act that way?
Yeah, because the bonds can rotate, and when you give something a fixed amount of energy, that energy rotates. Okay, so bonds can stretch, right, and they can bend, and they can rotate, right, and stretching and bending is what we're typically seeing in infrared spectroscopy. Remember the quantum energy levels for an electron? It turns out there are quantum energy levels for vibrations and rotations as well. And it turns out if you put energy into them, that's what they'll do. It has a degree of freedom to move in that direction, and so if it has the correct amount of energy, it moves in that direction. I don't know, that's maybe the easy way to say it. Okay? So, yeah, or the simpler way to say it is because it can. All right? If I gave you $1 million, you would go out and buy like some useless thing, and somebody will say, "Why did you buy that?" And you'll be like, "'Cause I could." There's not like it's just part of the behavior of molecules or people. All right, sorry. So so the old explanation would be the one that I learned in school, okay, was the reason there was that big energy difference between the staggered and eclipse conformations is simply because these groups, the hydrogens on the end, repelled each other. Turns out the actual answer is a little bit deeper than that. If you have it staggered like this, you have to think about what the orbitals look like for these two. Okay, there's a bonding orbital here and an anti-bonding orbital that sticks out of the back here, and it turns out that the overlap in the bonding and anti-bonding orbitals is better between the two atoms if it's like this. And so what they're showing actually in this molecule is this, and that you get this overlap between the bonding orbital sorry, the bonding orbital of one, and this is the anti-bonding orbital of the other. What that allows the electrons to do is it allows essentially the electrons to delocalize through space a little bit, and it causes it to be more stable, just like delocalization in general allows things to be more stable. The ability for the bonding molecular orbital to the hydrogen here to overlap with the anti-bonding molecular orbital with the hydrogen over here causes it to be a little bit more stable.
Why is the hydrogen on the right side half red and half blue?
Because it's an anti-bonding orbital and has a node. I don't know how to explain it other than that, but yeah. Okay, so it should look something like this orbital over here, but because it's an anti-bonding orbital, right, the phases of this atom and this orbital are different, and that's why they cancel out, and that creates this extra node. That's why it has that color. I'm sorry, it's being really flippant, but that's why it has that color change right there. It's a cancellation of the orbital density between those two. Okay. Yeah. Oh, yeah. So, hang on. I want you to think about this one now. Now I'm going to take butane. So again, I got to build a model. And I think it takes me a while to do this, but I think it's really instructive for you guys, for me to actually build this full molecule. Because you don't realize until you see it how big a methyl group really is in comparison to like a hydrogen. Of course, I'm going to have to, I'm just going to use a green one. I have a lot more. Green is not the right color, but. Oh, sorry, this takes a while to do. You can see me putting it together. Now, that's butane, right? You don't usually think about it, but that's what a hydrogen will look like. It'd be like this big. This is methyl, okay? So now what we're going to do is we're going to look at interactions down the 2-3 bond. We'll go from this direction, 2-3 bond. And this is staggered, right? And the large groups are far apart. But if I bring this group around like this, what happens? Right? When these rotate, they're actually almost close enough to touch. So there's a lot of strain that's created when this molecule is in the fully eclipsed position like this. Because this group is so big that it's actually close and almost touching to this group. Same thing is true, though, when you go to the 120 degree eclipsed. Not so much so, right? There's a little more room because it's now interacting with a hydrogen here and a hydrogen here. So the lowest configuration energy really is this one that's down here, where now these two groups are across from the methyl group, but they're further away than when they're eclipsed, because they're not like that. Go ahead.
And that's what that's
I think it's more than that now. It's like 99.9%. Because the energy is a lot higher for this versus this. Okay, now, let's look at something really quick. Okay, I'm going to do the Newman projection for it. And so I'm going to draw this on the board. Okay? And what we're going to do is we're going to draw the Newman. So to draw the Newman, I'm just going to draw a circle to start with. And I'm looking down this bond axis here. Okay, so the carbon in front of me has 2 hydrogens in a methyl group. Where's the methyl group pointing? Straight down. It's in the plane, straight down. This is in the plane along this axis here. So I'm going to start in the middle and draw a line down like this. And I'll put a CH3. Where are the other two groups in the front? Up to the left and up to the right. On the paper, we're drawing a bond angle of about 120. Recognize that it's actually 109.5, but because we're looking at it in the 2 dimensions rather than in the 3, it's flattened out, so they spread a little bit. But these are hydrogens. Now, part of the molecule that's in the back, okay, is this carbon. That's the carbon you don't see, or sometimes they say it's the point in there and all that kind of stuff. Anyways, sorry. Which direction is the carbon in the back going? I'm looking down like this, right? Like this. This is all in the plane, right? So this one is going up through here. So I have a CH3, and then here I have an H and an H. So this is the carbon in the front, right? These are attached to the carbon in the back. And now I'm going to have to tell you this horrible thing. I always consider that this circle, right, is the carbon in the front, and it's blocking out the ones in the back. And a lot of books and a lot of people say it's the carbon in the back, and these are the things sticking out of the carbon in the back. Okay. But it doesn't matter, because it's just a circle, and these are still the ones in the front, and these are still the ones in the back. So it doesn't matter. Okay. But you're going to read that. Just don't let it confuse you. To me, it's always made more sense that the carbon in the front would be big, right? And the carbon in the back would be eclipsed by, because you're looking at it like this in front of your eye. Okay, it doesn't matter. So this is staggered. We're going to draw another staggered configuration. Oh, let me try something. I saw somebody once take a picture and stick it on their dossier, but I'll have to figure that one out. We're going to rotate this 120 degrees, okay? So I'd like to leave the one in the front the same all the time and rotate the one in the back. Okay? You don't have to do it that way, but when I do these things, that's what I'd rather do if I can. Okay? So there's the circle. I'm going to still draw it like this. And in the front, I'm going to put CH3 at the bottom again, H and H. And I want to rotate the molecule in the back 120 degrees. What does that mean if I go clockwise? I take this group here, and where do I move it? Down to here. So this will be the CH3. This will be the H. And this will be the H. And then I'm going to rotate it again. More systematic. Again, CH3 in the front, at the bottom, H, and the H. And we rotate 120 degrees. Again, where's the CH3 end up? This one here. And H, and H. If I do it one more time, I'm back to the original one. I've gone 360 degrees, right? So these are all staggered. There's different names for them. Some people always say this is staggered 120, but what I'm going to call it, or staggered 60, I'm going to call it gauche. That's the common word for it. And this is also gauche. Gauche is a French word for, like, means in passing. Something like that. It might be that. Oh yeah, no. It's got this other funny. It's the awkward feeling you get when you pass close by to somebody or something like that. It's some weird French term. So like you have to think about what's happening as this group moves from here to here. He feels the repulsion, or she feels the repulsion. I just put genders on things. Feels the repulsion as it goes past, that awkward feeling as it goes past. Like, oh, I'm repulsed by that thing a little bit, and I will just slightly go past it. Okay, so that's what it means by gauche. Okay, now, oh, sorry. The diagram looks like this. All right. I should have done the one in between first, but I got a little carried away. So when the molecule is eclipsed at 0, so this is known as eclipse 0, okay? That energy is 19 kilojoules per mole. That's as they pass, they go from gauche position to gauche position, right? As they pass through each other, in between these two positions, the energy of repulsion that's created is now 19 kilojoules per mole, higher than when it's eclipsed at 180, okay? 180 degrees apart from each other. The gauche positions, that's these ones, are only 3.8 kilojoules per mole higher than here. And remember, when we're talking equilibrium, it's not the absolute amount of energy that matters. It's like how energetic is this relative to the base, right? But when you transform from the gauche, right, from, let's see, how are we doing this one? Yeah, when you transform and you take this and you rotate it like this, right, and go up to this, now you're at the 180, that's here, so you're rotating. The energy is now 16 kilojoules per mole. So those are all very high. Okay, so where do you think it spends most of its time? It'll spend most of its time in the 180. And if you wanted to calculate it, what would you do? All right. Oh, sorry, I'm going to skip some of these things. All right. You could take the energy, like the energy difference. Oh, sorry. Yeah, back up. You could take the energy difference here and do the delta G is equal to minus RT ln K, and calculate the fraction of time, like the equilibrium constant, for how much time it spends in that position relative to eclipsed. Or you could do the same thing if you wanted to know the energy or percent of time difference between these two. You could just calculate that. Okay, and it's always the same equation. You just plug it in, calculate the equilibrium constant. Okay, so I've always debated whether or not to teach this section. I'm going to skip over it again, and we're just going to practice drawing. Okay, so we're going to draw the Newman projection for the highest and lowest energy conformations of 2,2,3,5,5 pentamethylhexane. It's like, what is that? So how are we going to do this? Well, the first thing is draw the parent chain, all right? So it's a hexane, so we're going to draw 6. I'm going to do bond line, so 1, 2, 3, 4, 5, 6. And now it's 2, 2, so 2, 2, 3, right? 5, 5. I think this is named wrong. 2, 2, 3, 5, 5. Isn't that named wrong? Wait. should be 2, 2. No, that's right. That's right. Never mind. That's correct. Okay, and then we're going to look at the Newman projection between C3 and C4. So if you're going down to C3, C4, you're going 1, 2, 3, 4. We're looking in that direction. Okay. All right, so draw 2 circles. There's actually a couple of different answers for this one. And draw our bonds. And so now we're looking at carbon 3. So this is 3 right here. Okay. On the carbon number 3, what should I have on it? I should have a methyl, right? I should have a hydrogen. So I could put the, let's see, I'll put a CH3. Since there's no indication of whether or not there's a bond or a wedge there, you can put them in any order. That's why you can end up with a couple of different answers, okay? So I could have a CH3, I could have an H. What's the other thing going to be? No. This, what is this? It's an ethyl with 2 methyl groups on it, right? Does that sound familiar? Dimethyl ethyl. It's a T-butyl group. So just to make life easier, not draw the whole thing, I'm just going to do that. And then down the back, okay, I'm going to have 2 hydrogens. So this is on carbon number 4. And then what am I going to have? Another T-butyl group, right? Okay, so high and low energy configurations, right? This is the low energy configuration. Why is it the low energy configuration? The 2 biggest groups, the bulky groups, right? Talking about bulkiness. The 2 bulkiest groups are far away from each other. Okay. If you're not sure, what you should do is you should draw the other possibilities where you replace this hydrogen with a T-butyl, and then you'll see, oh, if I take this and move it here, now the T-butyls are next to each other, and it's next to the methyl group. Here it's just next to the methyl group, right? Then here, it's away from the methyl, but now it's next to the T-butyl. And in comparison, T-butyl is going to give more repulsion than a methyl group will. So it has to be that the position is down here. Okay? So if you're not sure, just place the large group in different positions around and look at what the interactions are. Okay, what would the highest energy configuration be? Yeah, but you notice it doesn't say the highest staggered. The highest configuration would be the eclipsed. So if I said the highest staggered, then the answer is to put the T-butyl group between the T-butyl group on carbon 3 and the methyl group. So this is the lowest overall. I'll draw the lowest staggered. The highest staggered. But the eclipsed is always going to be the highest. Okay? So the highest configuration, energy configuration, would have the T-butyl groups next to each other. So when you draw an eclipsed, okay, what you do is you draw this front like you normally would, okay, and then you draw the lines for the one in the back next to the lines in the front. And then you try to put the groups on top. So then I would put a T-butyl here, I put a T-butyl here. Let's see, I put a CH3 on the front here, and then an H, and an H. And having these 2 large groups next to each other makes it the least stable configuration. Questions? A lot of mechanics, drawing stuff, looking at things. Like I said, initially a model kit is really helpful, but in the truth is you shouldn't use the model kit as you're learning it, but you should also learn just to implement stuff in your head and be able to draw stuff as you see it, okay? And that's the hard part, getting to the point where you don't have to look at a model kit to draw stuff, okay? Okay, we'll talk about cycloalkanes. Cycloalkanes, carbon atoms that are all sp3, but in a ring, okay? What's the optimal bond angle for carbon with 4 bonds, sp3? sp, yeah, 109.5. 109.5. Okay, so you'll notice if they're all flat, if you should draw alkanes and you made them flat, that bond angle would be 60. That one has to be flat, right? Because it's 3 points and describes a plane. This one would be 90, this would be 108, this would be 120, 129, and 135. There's this concept of something called angle strain, okay? Molecules like cycloalkanes, where the atoms are sp3 hybridized, want to be at a 109.5 degree angle. So if they're not in a 109.53 degree angle, they will bend to try to achieve that angle. So let me build a cyclo something ane for you. I'm going to build as much as I can.
If they bend, if they strain themselves to create that 109.5 angle, would that make them least stable or less stable?
Yeah, so if they're all flat like this, you know, notice how this one's close to 109, right? If they're all flat like that, there's going to be some angle strain, because angle strain is defined as the strain caused by the angle being not 109.5 compared to what the strain energy would be if it was 109.5. So if you have a non-109.5 angle, either it's smaller or bigger, that causes strain in the molecule. So cyclohexane, 1, 2, 3, 4, 5, that's pentane, hang on. I've got to find one more tetrahedral center. And then I will get rid of, there. This is a fun one, right? So I'm going to try to make, now these are like mechanical, so they have to be at 109.5. I can force them to not be 109.5 if I do this, and I make it like that, that's 120, right? But what will happen to the molecule is the bonds will rotate so that they achieve a 109.5 degree angle. And then you can feel it in the ring when you build it. It doesn't have the strain, and the molecules move very easily. But when you get it to have strain in it, because the angle wants to change and the molecule can't, the holes, there's pressure in the holes. You can feel that pressure that's non-ideal. Okay? So you'll notice that in a cyclohexane, it's not going to sit flat. Oh, this one's not going to sit anyway. Is not going to sit flat because it wants to have 109.5 degree angles, okay? And that gives it less angle strain in the molecule. But there's a couple other things. Let's just really quickly go through this. Here's some energy data, okay? And what they did in the energy data is they said, okay, well, let's burn cyclopropane. And if you think about it, a cyclopropane is just made of a bunch of CH2 groups, right? Every cycloalkane is just made of a bunch of CH2 groups, as long as it's not substituted. So they took cyclopropane, they burned it, and they calculated the heat of combustion per CH2 group. They got 697 kilojoules. So if you were to put it on a graph, right? Let me make a little chart here, right next to it, I hope. So 1 or 3, sorry. Yeah, I want a 1 carbon ring. 4, 5, 6, 7, 8, 9, and 10. Okay. 697, I'm going to put that, let's see, 650, I think is where I want to go down to. So this is going to be 650, this will be 700, and this will be 1, 2, 3, 4, 5. Okay, so 697 for 3 carbons is up here, right? Let me use a felt tip marker there. Oh, holy moly. Hang on. I was letting my kids draw with this the other day. So the markers are all gigantic. Okay, 697, then 680, right? So 680 drops to here. Why is there a difference in energy between those? What does it imply about stability of the 2 molecules? There's more strain in the propane. It's less stable. Okay, so you have a lot of strain in the cyclopropane, and when you burn it, they all go down to per CH2 group down to some base level. There's a lot more strain energy in cyclopropane than there is in cyclobutane. Cyclopentane is around 660. Cyclo 3, 4, 5. Hexane is 653, so it's about 650. And then what happens? Cycloheptane, right? It starts to go up again. So 657, so it's around here. And then it's going to go up to 658. It begins to level off a little bit. 659. So you see the rest of them stay pretty steady until you get to cyclododecane, which is kind of cool. What's dodecane? 12. It's a multiple of 6, right? So it turns out once you get to 12, you can get back close to the 109.5 degree angle. So cyclohexane turns out to be, when it's in this particular configuration with the 109.5 degree bond angles, turns out to be the most stable of the cycloanes that we have. Okay, it's the most stable of the different cyclic alkanes. So this energy, right, above cyclohexane is typically considered to be ring strain. It's caused by the ring not allowing ideal angles in the molecule. All right, I think I'm done. I think I have to be done.